Yeah, thank you. So this works. Do you see the slides, or do you see my notebook?
I can see it perfectly.
Okay, very good. Okay, so yeah, this is about the iminuit library, and it's the library to fit models to data. And here are a few links. So this is a long-time member of scikit-hep. So a little bit of introduction before we go into the practical part. So iminuit is not only a front end to the MINUIT2 C++ library, but that's how it originally started. So you may know MINUIT. That's a famous code in HEP to do all kinds of fitting. So whenever you do a fit, it's usually MINUIT in the background that is performing the fit. So generally, it's a library to minimize statistical cost functions with box constraints, and that's what we use all the time. And what's special about MINUIT is that it can also compute parameter uncertainties. It has two ways of doing this. One is profiling likelihood, and the other one is computing a second derivative at the minimum. We will explore those later. And it's a really old library. I mean, not MINUIT2, that's a rather recent library, but the technology that's behind this is from the 1970s. But it's still a test of time. I mean, has not been replaced. So that's pretty good. And yeah, so iminuit is the Python frontend to the C++ code in root. So the code lives in root, but you can compile it without root. It's because MINUIT2 was originally a separate project that was later integrated in root, and they kept this kind of isolation, which is to our benefit. iminuit is not only a front end, so because when you have a Python code, you can do a lot of unit tests very easily, and eventually this also made us find some bugs, and so we contributed several patches also to the C++ part. So you guys also have something, get something out of this. If you're interested in history of MINUIT and iminuit, I recommend my previous HEP talk and 2 years ago. So iminuit is also only the latest iteration of several packages that have provided a wrapper for MINUIT. Okay, so, and I said it's not only a front end to the C++ code, because it also contains cost functions. And what that is, we will see later. So this is one of the two essential ingredients you need when you do a fit. And since these cost functions are rather technical and boring, and there's not much to customize, it's a good thing to put it into a library. And I decided to just put them in iminuit instead of making a separate package for that. Okay, so iminuit is not the only fitting package. So actually, maybe I can make this a little bit larger. So there's also PyHF and zfit in scikit-hep alone, and there are other fitting packages out there like I don't know, scipy, minimize. So why wouldn't you use it? Why would you use this one? So iminuit is rather low level. It's rather lightweight. It's fairly hackable because it doesn't impose a lot of structure, and that makes it easy to learn and easy to extend. So those are things you might like. And on the other hand, with the built-in cost functions, it supports all kinds of fits. So you can do binned and unbinned fits. You can do template fits. You can do penalized fits, and you can even simultaneously fit different data sets. I mean, this you can also do with other libraries, but yeah, maybe not all of these features at the same time. And the simplicity of iminuit is also nice for teaching, because yeah, I mean, you can still see everything that's going on mostly. That makes it also attractive for beginners and maybe also for experts. So for example, Glenn Cohen, I'm very happy to know or to have learned that he's using iminuit in his lectures on statistics. If you don't know Glenn, so Glenn has written yeah, a very popular introductory book on statistics in HEP, among other things, many other things. But there are a few things, because iminuit is supposed to be simple and low level, that are out of scope and that other libraries do better. So for example, there's no support for building statistical models. So when you want to fit something, you have to write a PDF yourself. You have to understand what a CDF and what a PDF is, and to use this library here. And there are other libraries that also help you with this part. Then there's also no such thing as automatic differentiation. So if you heard my talk from yesterday about Jacobi, you can speed up in principle this fitting process when you have some automatic differentiation, and that's not in the scope to provide that. So you can use that if you write your model in such a way, but it's not built in. So if you want to make sophisticated limits, then you should also use something else, because iminuit is not really, there's not much support implemented there. And there's also recently efforts in making the likelihoods that we fit storable, so that you can put them on the hard disk and somebody else can read it again and combine it with more data. So that's also not supported. So, I mean, and there are, of course, other libraries that provide these features. For example, PyHF is a library that is very good for bin fits and can do very, very complicated bin fits, a la histofactory. And it's very good for limit setting, and it can also store the likelihood. And zfit is, for example, a library that allows you to build the statistical models more easily, and you can also sample from the fitted model. So it's a bit like roofit in that regard. Okay, so that is all about the introduction. So let's dig into the tutorial part. So I think we should start with a simple line fit. So I import here NumPy, matplotlib, and also just for fun, this namespace class here from ArcParse, where you will see how that's useful. So I just generate some fake data so that I have something to fit. So I make 10 points here with some errors that are, 0.2, flat for all points, the same. And then I generate a line here, so with a slope of 2 and an offset of 1. And I also add these random errors here. So this funny call here is calling the normal distribution with these kind of errors, and it just samples me here some randomly displaced y positions. And then I put this is where this namespace thing comes in handy. So I can just put all these variables here into a little class that is automatically generated here by this namespace thing, just so that later I do not accidentally override my variables x and y and y. I put them in this namespace here. So, and then I can draw that. Let's execute this. So you see what I'm talking about. Okay, so that's the data I want to fit now. This should look familiar. So to fit this, I now need to provide a model and a cost function. So the model is basically what predicts the y values here for given x values for a given set of parameters. So in this case, this is a line. So it has 2 parameters, the offset and the slope. In general, models can have any number of parameters. And the cost function is the thing that tells the fitter how good how well the model fits this data. I mean, how far it is. In a sense, it's a kind of distance, but distance in quotes, because here, I mean, in this particular case, it's almost like a geometrical distance, but in general, when we do maximum likelihood fits, it's more complicated. It's a statistical distance, so to say. Okay, so what you can do with iminuit is you can write the cost function yourself. But we won't do this here, although it's very easy and you're very encouraged to do this. But for all these simple cases, they are now already built-in cost functions, and those have a few tricks up their sleeves. That's why it's useful to use them. So if you want to fit now, you need to import the minuit object from the iminuit package, and the submodule cost contains all the cost functions. Then I provide the line model here. So the model is always this structure. you get the x argument is the first one, and then the other ones are parameters. So this is usually a vector here, or yeah, can be a vector in general, and a and b are numbers. So and then it returns the y values for those x and a and b. And then the cost function takes your data, the errors, including the errors, and this model. And this object you can then put into MINUIT. So MINUIT receives this and some starting values, because MINUIT is using local minimizers. So you have to provide some starting value. This should be not too far away from the two values. And when I execute this, you will see some output here. In the beginning, MINUIT doesn't do anything. It just sets up the fit. So when you look at the return value here, which prints here as a nice table, you just see the initial parameters. So you can see that MINUIT recognized the values names here. That's not because I provided a and b here. I can also remove this and it would still work, because it reads those names from the model. So it's kind of magic how that works, but yeah, this works like almost all the time. And yeah, so it just starts with the values that we have set, and there are some errors here that yeah, we have to provide from MINUIT, but these don't mean anything. So they are more like step size, initial step size. This you can also set yourself, but you don't have to. You can just go with the default values that iminuit sets for you. So the way how to actually do now the fit is you call certain functions or methods. To be more precise, you call methods on this MINUIT object that I just called m. So this is the main way how you interact with the fit. So all the results are stored in this MINUIT object, and when you want to do iterative fitting or something like that, you always call methods on this. This is inherited from how C++ MINUIT works, and how the old, well, that's kind of how the style, how MINUIT operates, and iminuit just imitates that. Okay, so let's run the minimizer. So this returns something that you can't see here because I don't assign a value to this, but what it returns prints very nicely in the Jupyter notebook. So you get this nice output here, and it tells you a lot of things. And the green color here is good. That means there was no failure in the fit. So fits can fail, and we will come back to later why that happens and how to avoid it. So you see here the minimum value of the function that it fitted, and in this particular case, MINUIT was also able to compute a chi-square per degrees of freedom, which is 0.5, so that's pretty good. And you will see also here how many function calls it made, so that's useful maybe to see. I mean, if you start very close to the minimum, then this should be small. If you start very far away, then this will be longer, maybe more function calls, let's say. Yeah, so there's a question, can you comment on iminuit's ability to estimate fit errors when the parameters are highly correlated? I will come back to this. In a later part, we will look into this. So then there's this EDM value here. That may be a bit mysterious, but if you look into the iminuit docs, it's explained what this means. So this is the estimated distance to minimum. I can actually also point to this, and then you get this as a tooltip. That may be still kind of mysterious. So that's just how MINUIT works and how it determines whether the fit has converged. So, I mean, I suggest really to read the original paper to see what this does. But yeah, the point is this number has to be smaller than this goal here. And if that's the case, then the fit has converged, or at least MINUIT thinks it has converged. We will see later this is not always true, unfortunately. When you fit takes a significant amount of time, there's also a time flag here when it's very fast, and this is not there. And yeah, and here the other things here, all these green things tell you that everything worked fine. So if there's something not green here, then you should worry. We will see later a few cases. Okay, so now the output here shows the value that is fitted. So if you remember the model that we generated, A was 1 and B was 2. So it found values that are very close to that. And of course, they're not exactly the same because I added some randomness here. And then it also provided errors here. And the next thing that you can see is the correlation matrix for these parameters. And here you see the diagonal values, which are not so interesting, and the off-diagonal ones that are interesting because it tells you that your parameters A and B are fairly strongly correlated. So the first value is just the raw value in the matrix. That's not so useful, but the one in parentheses is the correlation. So that's the value between -1 and +1. And yeah, in this case, it's close to -1. So there's another question. MINUIT requires initial step sizes, which have to be guessed appropriately for the function as I understand it. Jacobi varies the step size. Can they be joined? Jacobi is not used internally in MINUIT. MINUIT has an internal way of computing derivatives. That's indeed how this works. So I didn't really go into the details, but what Migra does is it's computing gradients and also estimates some kind of second derivative. And when you have the first and the second derivative, you can do a so-called Newton step. And if your function is a parabola, or if the cost function is a parabola, then in principle you just need one of those steps with a perfect gradient and a perfect second derivative, and you are in the minimum of that function. And this is, of course, usually doesn't work because initially this estimate for the second derivative is very bad. And the gradient is also not perfect usually that MINUIT calculates, but the algorithm is built so that even with a bad gradient and a bad second derivative, it still eventually converges to the minimum if it's not too far away from that. So I'm telling you all this to make the point that you don't have to have a very good gradient here. Migra is already built on the assumption that the gradient is not perfect. So that's why it's not so useful, I would say, to plug something like Jacobi into it. The advantage of this very simple gradient that Migra calculates is that it's very fast. Jacobi takes much more time, makes a much better gradient, but takes longer to do that. So eventually this will be better for this particular case. So there's another point. I observed that least squares needs the data uncertainties. This is the chi-square. Yes. So I just decided to call it least squares instead of chi-square because in general, the least squares function doesn't have to be chi-square distributed. I mean, the value in the minimum doesn't have to be chi-square distributed. So at least in my opinion, the name chi-square function, which is maybe what you know from PyHEP, is a little bit inappropriate or inaccurate. So I call this least squares, but eventually it's computing the chi-square. That's also why when we go back to the, where is it? When we go back to the output here of Migra, you can see the chi-square with just computed for free here in this case. Okay, so a few other points. MINUIT computes the values here to much more accurate than what is shown here, but intentionally these numbers here are rounded to use the PDG rounding rules. Those are fairly complicated and but they are very nice because they really show you only the significant digits. So you see here lots of other stuff that I haven't explained. So the main error here that is already given is the one we call Hesse error. So it's a parabolic error. It's computed by inverting the matrix of second derivatives around the minimum. So this you get almost for free all the time from MINUIT. And then the other errors that are not computed here, which are these minus errors. And so when you want, if you want those, you have to call minus explicitly. We will do that later. Then parameters can have limits, so there are no limits set, so these are empty here, and parameters can also be fixed. We will see later why that is useful sometimes. Okay, so maybe another word. So when you're really in the minimum, then your matrix of second derivatives has to be positive definite. That's just a way of saying you are in the side, you are in the minimum of a parabola. If it's not parabola, For example, in high dimensions, you could be in a saddle point. So there's positive curvature in some direction, but then negative curvature in another direction. That's called a saddle point. Then this would be not true. It wouldn't be positive definite, and that's bad. I mean, you have to be in a minimum when the fit has converged for these errors to be meaningful here. So be careful that this is green. And sometimes when this is not working, MINUIT automatically tries to make the matrix positive definite, and then this last thing here, not false, this can be red. So that's also bad when you want to use the errors at all. Okay, so if you want to know more about these things, please look into the docs. So I wrote a lot of docs on all these things. Okay, so let's look at the output, the fitted values a little bit. So you can, I mean, this automatically generated large thing here can split up into parts. So when you just want to know the parameters, you can call m.params, and then you get just this part. I mean, this is actually a Python object that you can also query. It has many fields and so on, where you can read out all these values. When you want to know more about the function minimum, that's contained in this fmin attribute. So that has, for example, the chi-square degree of freedom, the time, the number of function evaluations, and so on. So basically what is printed here, you can also access via some attributes on that. Then the covariance you get like this. So you just call dot covariance, and this is NumPy array-like matrix. It's a little bit enhanced because it knows what the names of the columns and rows are in this matrix. And yeah, for plotting here, there's also something down to that. So now I told you that if you want to have the minus errors, you have to also do something explicitly, because this can be costly to compute. And but not in this particular case. Our likelihood is very, very small here and very fast to compute. So this doesn't take a significant amount of time. When you call this, you get this whole output again. But now you see there's these minus errors are now filled. And so this is an asymmetric, potentially asymmetric error. So you get two values here, one in one direction and one in the other direction. In this case, they are identical to these Hesse errors, except for the sign. Then there's this new output here that is coming from this minus calculation. So this can also fail. And when it's not valid, you will see some red here, and all these other things here. All this should be green. If this is not true, then there's some issue. Okay, so maybe you wonder. I mean, maybe you feel like, okay, let me tell you differently. So in the past, there was a time where it was stated that the minus errors are always better than the Hesse errors, and you should always report those. So nowadays, we have looked into this, especially in HCP, and it turns out that the Hesse errors are actually often at least as good as the minus errors, and they have the advantage of being symmetric and much easier to do error propagation with. So the more modern opinion is to actually, this is usually good, and only when these are very, very different from your Hesse errors, then you should report these asymmetric minus errors. So most of the time, you're actually better off using the Hesse errors, even if those are a little bit asymmetric. So when it's really, really, really important that you get proper errors, you should really investigate this more closely and also check coverage of these different error intervals. So this is just general advice that I'm giving you here. Yeah, so I mean, I told you that there are many ways of really using these objects to learn to get access to all those values. And here's just one example. I use this merrors dictionary-like property here to get the minus errors on the parameter A. And this returns a struct that has many fields, and you can query, for example, the name. You can query this valid field. So basically, this is what is in this table here. All these values you can check and then use for further computing. Okay, so yeah, maybe, I mean, for one thing that you should also often do, or basically every time do, is to actually draw the data and the fitted model just to see whether it looks good. because MINUIT can sometimes lie too. So this is what I'm doing here. So I draw the error bars again. This we have already done before. And now I also plot the model. And here I use the X values from the data. So this is convenient. Then here I have defined the model. So I can just plug in my X values here. And then I need the fitted values. And this can be done very easily by using, again, our MINUIT object and calling the attribute values. Actually, this is needed. Yeah. So the star here makes sure that this array-like object is unpacked, because our model, if you remember, it got 3 arguments, and we just take the other 2 arguments here by unpacking the values, which returns something like an array. So that's a very convenient syntax. So to access this chi-square, in this particular case, you can use this fval attribute. That is, in this case, the chi-square, but not in general. This is just a function value of the cost function of the minimum, but in this case, it's a chi-square. It's chi-square distributed. You can call this a chi-square. And you also get the degrees of freedom from MINUIT. So this is only, you can only do this when this is supported by the cost function. Again, the built-in cost functions support this in this case. So when this returns something that is none or infinite, then you cannot compute. I mean, then the function minimum is also not chi-square distributed. So that's the rule here. So if this is something finite, then this works. And you can plug in, for example, the chi-square degrees of freedom in your title and make a nice plot. And here I also add to the title just fitted values and the errors. So I do this with n.values and n.errors, and I plug in here the parameter names, which I get from m.parameters. And then this is just to draw the legend and the labels. So this is how it looks like. Okay, so you see, again, what I said before. So there's no built-in function in iminuit to do this plot here automatically. You have to kind of do this by hand. So this gives you a lot of freedom on the one hand, but if you have to do this a lot, you probably want to write a little function that just does this the way you like it all the time. Okay. There is actually a little bit of visualization built into iminuit since recently, and this is the so-called visualize functions. So the built-in cost functions all support this, but there are some limitations. So I cannot guess how you want to plot, for example, multidimensional data. There's too many ways of doing that. So this is only implemented for 1D data. But if you have 1D data, you can get a very quick plot just by calling your cost function, visualize, and then the parameter values. So here I plug in the fitted values, but you could plug in any other kind of values, and then this blue line would look different. So this is, of course, very useful to have a very quick plot when you are debugging. No? Then you don't want to make a production or the paper-ready plot. You just want to see how it looks like, and for that, that's the purpose of this visualize thing. That's also why it doesn't give you a lot of options to influence how this plot looks like. I mean, if you really want to do some serious plotting, you should call Matplotlib and do it yourself. Okay, so there are other ways to check that the fit was okay, and one is or built-in ways. There's another way. There's a built-in method to draw the profile. So, for example, around the parameter value A, and MINUIT then draws this. So that's the cost function here. It should be parabolic, roughly parabolic, and should really have a minimum where the minimum was found. And this gray band here is just a ±1 sigma error interval. So this looks all good. You can also do this for the parameter B. And this also looks very good. This is just because this problem is here so simple that, yeah, all the minimum, I mean, all the likelihood really looks parabolic. We can also look at the contour of this likelihood in 2 dimensions for the 2 parameters A and B. And this is how that looks like. These numbers here don't really mean anything. It's just, yeah, the minimum value +1, +2, +3, +4, and so on. These are not confidence intervals because I called here this function draw contour. This is a fast way just to see how the minimum function looks like. And yeah, this is plotted with contour lines. Okay, so there's a few other questions. Can you pickle the M instance so you can check later all the info? Yes, you can. Since a few versions already, you can do that. This is particularly useful also to, I mean, when you use the multiprocessing module in Python, and you want to return an iminuit object or you want to receive an iminuit object, this also requires pickling. And for that reason in particular, I made that. It's actually very tough. It was tough to implement because you have to somehow pickle the C++ instance in the background. Yeah, but I can be very tenacious. Okay, if you want to really have the confidence region, I hope you know what a confidence region is. It's if you make many of them and you repeat the fit with random data many times, then these confidence regions should contain the true value within a given well-defined probability. And the standard probability that people use is 86%. So if you want to have such a contour, you can also generate it, but not with draw contour, but draw MN contour. That MN is for minus. Because you have to actually run minus to do this. What minus does is really, I mean, here we only have 2 parameters, but in general we have more, and then it minimizes the function along all those other parameters and finds a certain contour in this kind of, yeah, special likelihood. We call it profiled likelihood. So now the meaning here of the number is really that this is a region that's containing 68% confidence. So in this particular case, you don't know what the true values are. I mean, actually, we know because we know the true values, so they're here. So this region actually contains the true value, but that doesn't mean anything. So I mean, you have to really repeat this fit many times with random data, and then this contour is mathematically constructed so that it contains the true value in this with this given probability. That's generally true for all the errors that we usually use if you can, I mean, if you're a frequentist. Okay, so yeah, there was also a question, how does iminuit know how often to scan the likelihood to profile? Yeah, that goes into detail how the minus algorithm works. It tries to do this efficiently. I think one could do this probably even better. I have some ideas, but I didn't have time to really implement them. Yeah, I mean, what it tries to do is it takes the Hesse matrix. So you already have a first guess how this profile would look like if it's really an ellipsoid. And then it just does some bisection to find this this value here. The next question is it possible to get the contour data as a list? Yes, you can. So if you just leave out this draw and you just do this call, for example, and you remove the semicolon, which I always add because this suppresses the output of the function, then you get these values here and you can draw them yourself. Actually, we do this in a moment. Can you explain the difference between draw profile and draw MN profile? Yeah, I tried. So what draw contour does, or draw profile, I mean, yeah, I explained the difference here between draw MN contour and draw contour. And the same also is there for draw profile and draw MN profile. So when you just draw the profile, which I haven't done here, it gives you, yeah, I have done it here. So we could also add here MN. And if you look, I mean, it looks almost the same, but the scale here on the y-axis is a little bit different. And what happens in the background is when I just call this, it just does a scan along the direction of B, and nothing else happens. So it's just evaluating the cost function as it is. But if I call draw MN profile, what it actually does is for every point here in B, it minimizes the cost function for A. And this is, of course, expensive. No? So you do a little minimization here for each point along this line. And that's why this is more expensive. But this is what you have to do if you really want to get this confidence interval. If you just want to check whether the profile looks reasonable, namely like a parabola, then you don't need this. And you can just do draw profiles. So for debugging, really draw profiles, what you want to use. And only if you don't trust what Minos has provided you, I mean, the numbers that they have provided, then it's useful to check draw and then profile. So in general, you don't need this for debugging. And likewise here. So I mean, the draw contour is for debugging, and draw MN contour is really when you want to publish this. No, this is you can publish this confidence region. Yeah. And of course, maybe you don't want to use our standard plot, but you just want to get the values and plot it yourself. Okay, so what you can see here from draw MN contour is that you get an ellipsoid which has this funny tilt. And that is reflecting basically what we have seen before in the covariance matrix, namely that the parameters have a negative correlation. So negative correlation means the ellipsoid is tilted in this direction, and positive would mean it would be tilted upwards. So correlations are not fundamentally bad. There was also a time when I learned that you should always construct your model so that the correlations are minimal. That's not really true, so it's actually fine. If these become very, very large, then this is usually more another issue, as we will see later when, yeah, what could be the reason why you have very, very large correlations between parameters. Someone asks also why this contour looks a little bit jagged. That's true. I mean, this is because of this finite accuracy with which Minos operates and tries to find the border of this contour. And it's also real. So, I mean, you can increase your the size, the number of points that is used to calculate. So you can make it, well, you cannot really make it less jaggedy. As you see, it's still a little bit jaggedy. But you can at least make it more smooth. So this is there's some default value when you don't specify the size, which I forgot what it is, maybe 50 or 100 points. So if you want to have it really, really smooth, you would have to really dig into the Minos algorithm and then make them better. Okay. Does it use linear population? Yeah, there's some kind of, yeah, not really. I mean, yeah, no, I mean, this plot here does linear interpolation, but this is a feature of Matplotlib. So the way how it connects the points is linear interpolation, yes. Okay, so where was I? Yeah, I wanted to show you something else. So if you want to understand what this contour here basically means is, so basically what this means is if you are kind of 1 sigma-ish away from the minimum, there's a certain combination of parameter values that shift your model 1 sigma away from the data. And you can actually visualize this with this little code here. So this is just to draw the model and the line and the data again, just very quickly. We have done this before. And now I do this readout that we already teased at before. So I really get a list here of all those values A and B that are along this ellipsoid. Then I loop over them. And I draw my model for all these different parameters. So I get actually lots of model lines here. So many that I have to set the transparency very low. I mean, high transparency. So, and then you get a plot like this, which looks suspiciously like an arrow band. But this is not a proper arrow band. Don't do this. It's just for illustration what these points on the contour line basically mean. So or each of them gives you a slightly shifted and tilted model line. So if you want to do a proper error band, there's a tutorial in iminuit that you can just read when you click on this link. And if you followed my talk yesterday, you may know about Jacobi already. So that's one way to do it. And another one is resample, is another library for me. These two you can use to make proper error bands. So I show you here how to do it with Jacobi. Again, draw the data and the model. And now I want to propagate the uncertainties that I got from MINUIT, which are parameter uncertainties. But now I want to know what's the uncertainty of my model. So I just take all the outputs. I mean, the output of a model is a vector, and I just want to know what's the covariance or the error of that output. So I have to use a little adapter function here, because propagate requests that the function that it propagates through just accepts one argument, and that is a vector of the parameters. So I cannot pass the x here. I have to use this with the lambda here. So this lambda just is an adapter that I can pass my parameters here as a vector. And here the vector is unpacked and the response of my model is computed, which is another vector. And that is basically what propagate needs. Then I plug in my values and my covariance, and then I get my values of the model and the covariance of those out. And to draw the error band, I need the diagonal of this. And the covariance is the square of the standard deviation. So I have to take a square root, and then I can just plot the error band like this. So I have here my x values, and I subtract to 1 sigma and then add 1 sigma, and I make it a little bit transparent. So it looks nicer, and that's a proper error band. Again, you see there's nothing here done automatically, so you can easily do it yourself. But if you have to do it a lot, you probably want to write a function that does this. But there are also other ways of doing this, and maybe you find the one that's using resample more appropriate for your use case. Okay, so many more questions. There's more of a statistics question is the way to get an effective degrees of freedom, being non-integer when the parameters are highly correlated. So I don't provide this. I don't know how to do this in general. I don't know a good solution to calculate this. I know what you're talking about, and I think it would be very nice to have. Yeah, but I mean, it doesn't have it at the moment. So another question is, there's a way of plotting asymmetric uncertainties that come from minus. I mean, if you get the errors, I mean, if you request the M errors, so maybe let's just do it. That's why this is interactive, right? So basically what this returns, you can use to also draw the errors. I don't have a nice example here. I don't want to do this just spontaneously, but when you use pyplot error bar, this also can accept asymmetric errors. So you just have to write a proper adapter for that. And then you can also read out and plug in your asymmetric errors. So I refer you to the documentation of this M errors attribute and how to get the errors out. So another question is, can Jacobi propagate work with a log likelihood model, or must it have an exact functional form? So Jacobi can propagate through anything. And in this case, we had a least squares function, but equally, it would have worked equally well with well, I mean, we are talking here about the model, yeah? So the model doesn't know anything about the cost function. It's independent of that. So you can propagate through any model in general, and it doesn't really matter what your cost function is for this. Cost function doesn't even enter here. So if you use one of the built-in cost functions, you can be sure, and I mean, if you satisfy all the requirements of that cost function, you have to read the docs. Then and you have a proper minimum, then what the covariance is returned here is really the error matrix. So, and then you can do this propagation. So that's how the cost function is important, but only in the sense of doing the minimization process and to give you the right uncertainties. Okay, so since drawing these profiles is kind of useful for debugging, I made a nice little function that does this automatically. So this is particularly useful when you have a plot, a fitting problem with many degrees of freedom. Then you can just call this, and it generates the 1D profiles and the 2D profiles for all the pairs of parameters. And I see now I used up a lot of time already, so I have to move on a little bit. But you had many interesting questions, so that was also good. So I want to say a few words about why fits fail and how to fix that. So we have to unfortunately move a little bit faster now. Okay, so one reason is if you use starting values that are poor. Poor means far away from the two values. That's, I think, the most common issue when you start fitting, that you don't know really how to find good starting values. And the reason why this fit fails is, I mean, in general, we fit maximum likelihood, and the likelihood is a product of probabilities, and then in the end, you take the probability of that. So if your probabilities are 0, because your parameters make it so that the data is very far away from where your PDF is defined, then you just get 0, and the logarithm of 0 is -infinity, and then MINUIT doesn't know which direction to go. It looks like wherever it goes, the function is just -infinity, so then it cannot really find a minimum. So that's why you have to start reasonably close to where your minimum is already. Then another reason, more subtle, so even if a function is not just -infinite, if you were very far away, then if MINUIT just does a small step in one particular direction, the change in the curvature of this function may be so small that it really doesn't recognize that it thinks it has already converged, although it hasn't. Okay, so to illustrate this, I show you here. Now this is an unbinned maximum likelihood fit. I generate some normal distributed data, and then I fit the normal distribution. By the way, I use the normal distribution here from NumberStats, not from SciPy. NumberStats has faster version. Unfortunately, I mean, the SciPy statistical functions are great, but they are very slow. So if you want to have something faster, go on NumberStats. Yeah, okay, so it's a normal distribution, so it has a location and a scale, so mu and sigma in our language, and that's what I fit, and I use a starting value here. So this random number generator generates a standard normal distribution with a mu of 0 and sigma of 1. So I also set the scale to 1, but the location here is set to 50 just to make it really bad. And you see now that fails, and you see this is not green, says the minimum is invalid. You also see that the EDM value, there's none, that's bad, not a number. And yeah, okay. And interestingly, Hesse says this is okay, and that's wrong. No, Hesse should also say that computation failed. As you can see, the errors here are also none. That's clear. If you have none to start with, any computation will also give you none. This is actually a bug in C++ MINUIT2, and we should fix this. And this is also a shout out to you. So when you see things like this, don't just shrug your shoulders and say, okay, software is just weird. Please report this, because I try to fix all these things. So, I mean, I think this should be, when errors happen and where you develop, a lot of errors happen. So the library should give you very good feedback on what the errors really are. And something doesn't work, it should give you a proper error message. So I think it's a great way to contribute to the hacker shop, just reporting all the errors that you find with simple reproducers, so I can actually understand and figure out what's going on. So just to illustrate why this is happening, so our model is over here, and our data is over here, and just for numerical reasons, the PDF starts to become 0 here at the value of 30, so about 20 units here away from the location. And there's also, you can see this more explicitly here. I just call the PDF with a mean of 0 and sigma of 1 at several values in C, and 1 and 10 it's still defined, and then for the other far away values it's just returns 0. It's just because floating point numbers cannot be smaller than 10 to the minus 333, I think, and these numbers are smaller, so it just returns 0. Okay, so we can fix this just by using a good starting value of 0. And then you see, okay, now it found reasonable values, everything is green, so this is fine. So how to get better starting values? I mean, there are many ways. So, I mean, one way, if you have simulation, you can maybe just use the starting values from simulation, even for your data, if you have scaled the simulation appropriately. And other ways is sometimes you can do a simpler fit and then use this as the starting point for a proper fit. So, for example, these squares fits are generally very robust, even when you are far away from the maximum. And you can start with this and then use a maximum likelihood fit as an afterburner. The reason why you can't use it just least squares fit all the way is, at least for Poisson distributed data, which we usually have, this is an approximation and you really have to use the maximum likelihood thing. Okay, so this problem here is not only academic with this Gaussian that I fitted, but you can also have this in more practical situations. We do a lot of signal plus background mixture models. So I generate here some normal distributed signal and an exponential background, and just plug this into my namespace here again for convenience. And here I plot you this. So this should look familiar when you do ING physics. Now you want to fit the peak here. The background is usually not of interest. So we do an extend bin fit. And if you don't know how this works, you can always ask the help. And the help is very extensive. It tells you how to provide the parameters and how the model has to look like and so on. So in this case, our model looks much more complicated than before. So again, the X values are provided here as the first argument, and then it has 5 parameters: the yield of the signal, the mu of the Gaussian, the sigma of the Gaussian, the yield of the background, and the slope. I mean, this background was an exponential, so it only has a slope parameter and an amplitude. And now I use here the truncated normal distribution and truncated exponential because my data is also truncated. So this we often forget. But I mean, here I cut at the values. So I mean, that's also what you usually do. I mean, this is an invariant mass distribution. You only look at the slice. You don't look at all possible values. And then the proper way to handle this is actually to also use the truncated distributions for fitting. Often this, you can get away with not using the truncated ones, but in principle, this is the proper way. Now we need a different cost function. This is the extended bin likelihood because we want to fit bin data now. And it's extended because we don't fit fractions. We really want to fit the yields. Because, yeah, this is not a fraction. It's just an integral over the PDF. And I provide the bin counts and the bin edges and the model. And then this gives me my cost function. And I plug this into MINUIT, and then I have to choose starting values. And here again, I chose poorly because my mu is here at 5. I mean, you can see already by eye that the mu has to be around 0.5. So I'm factor 10 off. And that's why I get here again my not a number and everything is bad. And the reason is if I just call the function really at those points, it already returns none. So I mean, there's no way that MINUIT can recover points. Okay, the solution is again just to use better starting values, of course. And but another thing that is important here, and why I choose this example, here we have now parameters that we really need to constrain. So, for example, the sigma parameter of the normal distribution, it cannot be negative, and so you have to provide some limits. And this is done with this limit attribute here. You give the names here of the parameters, and then this is a one-sided limit. And this you really have to do. I mean, yeah. I mean, if you provide a negative value of sigma, or MINUIT just stumbles into a region where this value is negative, this is just not defined, and then you will get none for sure. Also, the yields, they have to be positive, cannot be negative, and so on. So I have to really move up because, yeah, we won't have time for questions. But I want to show you a few more things so you can also visualize this. In this case, I seemingly got a good minimum here, but the chi-square was bad. It's 4.5, not close to 1. And when I visualize the result, I can see also why. I mean, somehow the background here was not fitted properly. And that's why you should always check also this the fit result. And I can now also use the draw profile to see what's going on. So around the signal yield, it looks actually quite nice. And when I look at the slope, I see where the problem is. So this is not a minimum at all. This looks like a line. No? So this is not parabolic. So this is bad. I mean, the problem is here, why did MINUIT say it's converged when this is obviously not the case? So just because this EDM criterion is also not perfect. Maybe we can fix this. I have some ideas how to do this. Okay, so to solve this, we have to also put some strong limits on, or stronger limits on slope. Before it was just has to be positive, and now we say it has to be between 0 and 2. And when we do that, we get a good result. So now the chi-square is 0.9, which is very close to 1, and we are happy with that. We can visualize this and it looks okay. And we can draw the MN matrix. This takes a moment. Gives you a nice progress bar. And then you see all these profiles here, which just look beautiful for this case. Now you see these are not perfect ellipsoids all the time. This looks more like an egg. That's how it is. So the last reason why you can, yeah, okay, I guess I have to skip this. I mean, another reason you can have an ambiguous model. Okay, very briefly. So this would be one example where you have too many degrees of freedom. So this is a line, but you have provided here 2 offsets. And when you have that situation, I can just make B arbitrarily small and compensate by making A arbitrarily large. And this creates an ambiguity, 2 perfectly anticorrelated parameters. And when you try to compute the Hessian, this still works, but the Hessian doesn't have full rank anymore. And when you try to invert this, this cannot work. I mean, if you try to invert a matrix without full rank, you don't get proper errors. And so I just execute this, but we have to skip all this because I'm running out of time. There are ways to fix this. You can apply some penalties to resolve this. You can fix the parameters that are superficial. And yeah, just to, this is the very last thing. I wanted to show you the interactive mode. That's also very useful. So I just to play around with this. You can just, when you have a 1D fit, you can just call MINUIT interactive and then draw some sliders and see how the model changes. And you can fit it also, or you can fix, optimize certain values and then just change the others and see how this changes the fit. That can be very educated. This is very jaggedy here in a Jupyter Notebook. When you do it in VS Code, it's very smooth and nice. The very last thing I have to skip over is there's also a way to do a BarlowBeeston template fit recently. A template fit is when you don't have a parametric model, but your model is also a random histogram that you got from simulation. You can also now fit this. There was a cost function added for this. And yeah, I mean, now your model also has errors because it's a histogram, so it has statistic errors. And these BarlowBeeston-like methods, they include that error in your fit. So when you fit this with such a histogram model, you get additional uncertainties that come from the fact that the model is not well defined. Yeah, and I suggest to read a little bit here more about the points that I made, all these nice references where this is explained better. You can also do this interactively, of course, and see how things change when you change the yields. And with that, I would close. Sorry, one minute too long. If you want one more, please look into the tutorials and the studies that I have in iminuit.
Okay, thanks a lot for this very nice, very useful tutorial, and also thanks for staying in time. Since we started 2 minutes late, I think there's time to maybe answer one or two more questions on Slido, and then we can move the rest of the discussion to Slack.
Okay, so maybe Eduardo, you can comment. So you said at some point, what would happen if you try to plot at this point? At which point?
Yeah, I mean, when you gave it a completely different new completely offset, so there was no way you would have convergence. And then I was wondering, yeah, a few bits before. So if you were trying to plot before actually, but when fit was not converging everywhere. Yeah, above this thing basically. Went fast, right? I think it was roughly here, right? Exactly. Well, When you had a none, sorry, when Hesse was saying okay, but you actually had a none as a value.
Yeah, I mean, then it will just plot nothing because when it tries to evaluate the model, since one of the parameters is none, then the model would also return none, and then I mean, Matplotlib just doesn't draw anything when it has none values.
Ah, okay, of course, yeah. All
so
right.
that wouldn't be very helpful. You would just see the data, but no blue area. So.
Yeah, exactly. I was not seeing a way of plotting it, but just wondering how that would work out. Okay, thanks.
Then there's a question, MINUIT, whether it supports unbinned fits with data with weights. So not unbinned fits, but when you have bin fits with weights, that's supported. And unbinned fits with weights are complicated, so we don't support that right now. The reason is because you cannot, the way how MINUIT calculates the errors doesn't work for an unbinned fit with that's weighted. You have to actually use a different way of calculating the uncertainties for your parameters. That's not supported by MINUIT. So maybe we will support this in the future, but it's kind of a little bit out of scope of what MINUIT can do.
Okay.
So
I think maybe we
I guess
move on with the next presentation.
Yeah, I can just answer more questions later in the chat.
Yeah, thanks a lot. Yeah, we will post them on Slack and can.
Yes, Slack better. We'll move the questions to Slack.
Yeah. Okay, then